Ethene, commonly referred to as acetylene, is an important feedstock for the synthesis of a variety of organic chemicals and polymers. It is mainly produced from the steam cracking of hydrocarbons or partial combustion of natural gas. In such processes, CO2 is a co-product and needs to be removed to produce C2H2 that is desired by industry. Industry demands C2H2 purities in excess of 99%. And in this presentation, we examine pressure swing adsorption technology for C2H2 CO2 separations and how to evaluate MOFs for use in such PSA units. The separation of mixtures of ethene, C2H2, also called acetylene, and carbon dioxide is important industrially for production of pure ethene. Typically, the purity requirement is 99% plus. A PSA scheme for using an adsorbent that selectively adsorbs C2H2 is shown here. It consists of pressurization, an adsorption cycle in which rich CO2 is removed at the top, followed by co-current blowdown, and final countercurrent vacuum blowdown to recover the desired high purity product. Any CO2 that is remaining in the void volume and inside the pores will contribute to lower purity of the product. In order to achieve high product purity at high recoveries, it is important to choose an adsorbent material that practically rejects CO2 entirely into the gas phase and does not adsorb CO2 at all. Let us compare 9 different MOFs for separations of 50-50 mixtures of C2H2 and CO2 at a temperature of 298 Kelvin and a total pressure of 100 kilopascals. As mentioned in the foregoing slide, the best separations are achieved by MOFs that practically reject CO2. This allows high purity C2H2 to be recovered in the vacuum blowdown operations. I plot here IAST calculations of the CO2 uptake versus the C2H2 uptake on the x-axis. FJU 90 has the high uptakes of both C2H2 and CO2, whereas SOFOUR-TEPE-Zn, which is a sulfate-pillared MOF adsorbent using 1122 tetrapyridine 4-yl ethene, which is the TEP ligand, with dense electronegative pore surfaces. This MOF is described in this paper just published online in Advanced Materials 2023. This is the digital object identifier. You can look it up. ZNU1, which is also an important MOF, is described in this Angewandte Chemie paper published in 2021. Just to repeat what I said in the previous slide, we would like a MOF that has a reasonably high uptake of C2H2, but it is important that the CO2 uptake be negligibly small. On the basis of the IST calculations shown here, it appears that SOFOUR-TEPE-Zn, that is described in this advanced materials paper, is likely to be a prime candidate for use in PSA separations. Just to compare, the breakthroughs in the adsorption phase for the two MOFs, ZNU1 and SOFOUR-TEPE-Zn, shown in blue, we see that due to the very low uptake of CO2, the CO2 breaks through into the gas phase significantly earlier than the corresponding breakthrough for CO2 with ZNU1. Also, with SOFOUR-TEPE-Zn, the breakthrough of C2H2 occurs later. I show here by arrows the times at which vacuum blowdown is to be initiated. These times are chosen to be just before the times at which C2H2 breaks through. The x-axis in this case is a modified time parameter, that is the product of the volumetric flow of the gas mixture at the inlet, Q sub naught, times T, the actual time, divided by mass of adsorbent. The units of this is liters per kilogram. And the y-axis is the dimensionless concentrations of the components in the gas phase exiting the adsorber. Now, let us examine the recovery of the two products C2H2 and CO2 from the vacuum blowdown operations. I now consider the vacuum blowdown operations for 9 different MOFs that were listed in the foregoing slide, and for which the IST calculations were presented. The green lines are for FJU90, that has the highest uptake of C2H2 and CO2. And so in the blowdown operations, the recovered C2H2 in moles per kilogram is plotted against a modified time parameter, which is the product of the desorption flow rate that is dictated by the vacuum pump used in the vacuum blowdown operations, times T, the actual time, divided by the mass of adsorbent in the bed. Again, the units of this modified time parameter is liters per kilogram. The MOF FJU90 has the highest recovery of C2H2, but concomitant with the high recovery of C2H2 is a relatively high proportion of CO2. You can see the so what you would like is a MOF for which you have a high value of C2H2 recovery, but the CO2 in the vacuum blowdown is so low as to allow high purity C2H2 to be recovered. So you need the MOF to be high in this parameter, cumulative C2H2 from blowdown, but low in this. And I would invite you to look at this MOF SOFOUR-TEPE-Zn shown in the black solid lines. This is the lowest CO2 recovered after blowdown, and a reasonably high value of C2H2, second only to FJU90. But the FJU90 has the disadvantage that the CO2 recovered is also very high. If we plot the C2H2 purity in the exit gas after blowdown, we note that SOFOUR-TEPE-Zn has the percentage C2H2 in the gas during vacuum blowdown reaches 99.4%. That is slightly above the industrial targets. FJU90 has one of the lowest purity requirements. So of all the MOFs that were evaluated, the ones which are likely to be of commercial interest are SOFOUR-TEPE-Zn, shown in black here, and shown in cyan is ZNU1, where the purity is not just is about 96-97%. This can be raised with process optimization scheme by adding additional beds. But in my analysis, the first two MOFs are shown here, and likely to be of industrial interest.